beams, and I can aim them independently, and each one of them carry a separate message. And if you don't believe me, except that it's acoustic, not electromagnetic, that's exactly what you're looking at here with a line of speakers. There's an example for this torch sitting right here. Okay, isn't that fascinating? Okay, it's a multi-beam acoustic phased array. Okay, so again, if I've got 10 antennas with the right electronics behind it, I can make 10 independent signal beams. So I could reuse the radio spectrum 10 times. So I've got even more bandwidth capacity. But you're a skeptic, so you're saying, well, hang on, I can do that at any frequency. I mean, this is doing it at audio frequencies. Yes, but the element spacing to do this needs to be half a wavelength. So if your wavelength is like this, 150 megahertz, your array is going to be crazy big. But if we do it at a high frequency, the wavelength is small, and we can build an array with many elements to make many signal beams, to reuse the spectrum many times, and it can still be nice and small. So that's the argument. We can do that with it. So again, a lot of spectrum, and we can use it many, many times. So 100 gigabits per second is easy. We can easily talk about a terabit per second. All of that sounds fantastic, but there's got to be a price, and there really is a price, and that is that the propagation range is really, really short. Two reasons. One is lambda squared over r squared Friss path losses. What the heck does that mean? Diffraction. The beam spreads out, and you lose signal energy, and the higher the frequency, the worse it is. That varies as frequency squared. Okay? The other is that's under good weather conditions. Under bad weather conditions, the atmosphere has a lot of losses, and that makes it even worse. So in combination, the range is very, very short. So to make this thing work at all, we need arrays with many, many elements, as we're going to see. We need the receivers to be very, very sensitive, which is to say low noise figure. We need the transmitters, well, maybe not powerful for each element, because we've got a bunch of transmitters, but we sure need them to be very efficient, because overall we've got to radiate a lot of power, so we don't want to burn lots of DC power. Okay, now if we're going to understand each other, we've got to do about a common, 10 minutes of classwork, okay, or 5 minutes or something. How do radios work? What are the limits? If I've got a radio link, I can transmit signals. Sunny, I lost my equal sign there, I don't know why, but that's an equal there. I can transmit on a carrier frequency. I can break that carrier frequency into both sine and cosine that we call, for some reason, I and Q, and I can modulate each one of those with +1, -1, so that's 4 combinations. That's called quadrature phase shift keying, or QPSK. Little bit of math shows that the receiver sensitivity is basically the thermal energy KT times a signal-to-noise ratio of about 10 times what's called the noise figure of the receiver times the bit rate. Okay, so that's basic radio sensitivity formula. If the catch with this kind of modulation is it only gives us 2 bits per second of information capacity for every hertz of bandwidth that the government lets us use. Usually they don't give us a lot of bandwidth, so that's not enough. So we'll use multi-level signaling to get more bits of information in that bandwidth. So we can get more bits per second for every hertz of bandwidth if we use multi-level signaling, but it comes at a huge price. The sensitivity of the receiver degrades exponentially fast, which means that the transmitter's got to radiate exponentially more power. Okay, trade-off between power and spectral efficiency. Okay, next thing is what's the path loss between transmitter and receiver? I mentioned that varies as lambda squared, which is to say as one of the losses goes frequency squared. High frequency systems are worse. We can beat that by using arrays of radios on receive and arrays of radios on transmits, and the ratio of receive to transmit power varies as the product of the number of channels we have in the transmitter times the number of channels we have in the receiver. That's how we save ourselves. All of that's fine, but it's worse. We've got atmospheric losses. And no one will be happy if your cell phone only works half the time. You're going to want your money back, right? You're going to want your money back if your cell phone fails 1% of the time when the weather's bad, right? Because that's when you really need to call someone. Come pick me up, right? You can't say, I'm going to engineer a system so that it works most of the time, just not when it's raining like crazy, right? Sounds good as an engineer, but as a customer, you're going to be furious. So these systems are generally engineered to give you failure probabilities of 10 to the minus 4 to 10 to the minus 5, or in the industry jargon, 4 nines to 5 nines of reliability. Okay, maybe not here in Campinas, but in Tokyo or Southeast Asia, at 4 nines probability, it can rain 50 millimeters per hour. And that gives you loss varying as frequency to the 4th power And oddly enough, it levels off and goes flat. That's because of the raindrop size, roughly at 50 gigahertz. Okay? What's interesting is above 250 gigahertz, that's not your worst case bad weather. Your worst case is actually a nice sunny day. It's just ridiculously humid. 90% humidity, 35 C. That's the black line, and it goes rocketing up because of molecular absorption of water. So people talk about terahertz radios and say in space maybe, but on planet Earth, you're smoking crack. Because you're talking 200 dB per kilometer. You're going to have to radiate a megawatt. Okay, we don't need a radio. You can just see the glow in the distance. Okay, you got it? All right, so, oh, what just happened? Okay, all right, that was scary. Okay, all right, well, I'm awake. Okay, now the next thing we talked about arrays of transmitters and receivers. So here I've got a radio with many, many antennas, each with the radio channel behind it. And it's receiving signals from all of you coming in different directions. So every antenna has a mixture of signals from everybody it's talking to. So how do we sort that out? And it sounds really, really scary, except if you've taken a basic course in optics, you know the electric field as a function of position here is simply the Fourier transform, not the temporal Fourier transform, the spatial Fourier transform of the electric field as a function of position coming in different directions. So all the receiver has to do is take the signals, take them from high frequencies down to baseband, digitize them, and digitally compute a spatial Fourier transform. And now it knows signals coming in different directions and can sort out your individual conversations. Okay? Finally, high frequency signals are easily blocked. I've got a radio and I'm sending a signal from me to you. Boom. It's like that. It's like a laser beam. What's going on? How big an object will block the signal? And the answer is, it's an area called the first Fresnel zone. There's an area that's roughly the product of the wavelength and the distance, and that's where the energy is carried. So if your wavelength is small because you're at high frequencies, your beam is easily blocked. So you've either got to protect the path, or you've got to have many ways of getting the signal to the end user. Am I talking too fast? Crazy fast? You got it? Okay. All right. Okay. So we had many different problems that I described to you that this 60-student, 20-professor center had to attack. So we said, let's have two organizing projects to force us to attack all of these problems. So maybe the system that I'm building, that we built, was not really what industry would be building, but it's designed to force us to attack all the main problems. Is that clear? So the first is, let's build a base station. Let's use 140 gigahertz. Let's have each base station talk to 16 people on the ground. Let's each have 32 antennas with the electronics behind it. Let's assume that in the handset, I need 3 hands here, there we go, that we've got a similar array with 64 elements. At a half wavelength, that's about 1 square centimeter. Not too bad. Okay, let's do a link budget. Okay, let's assume that we're talking at 50 meters range. We're giving everybody 10 gigabits per second each. Goodness knows what they'll do with that. Okay, it's raining really hard, 50 millimeters per hour. That's our 4 nines condition. Okay, we're going to be sensible like industry. So we're going to give ourselves 16 dB safety margins for partial beam blockage, manufacturing variations, and the equipment getting old. This is real world. Okay? Then if I do a link budget, if my receivers have 7 dB noise figure, which is to say they're 7 dB noisier than the thermal energy KT, then each one of these transmitters needs to put out about 18 dBm. That's about 75, 80 milliwatts. Okay, so like, fine, what does that mean? Well, what that means is these numbers are very boring. You can do these numbers in CMOS, so there's absolutely no question you can build a system. The question is, how much does it cost? And does anybody want to use it? Okay, got it? Next concept system was the backhaul. I've got one telephone pole talking to another telephone pole. I'm going to use a 200 gigahertz carrier. If I look more closely at the telephone poles, both the transmit and receiving telephone poles have 8 transmitters on it. So each 8 transmitters, 8 receivers. Each one of those transmitters, I'm going to have radiate 80 gigabits per second, so my overall data rate is 600 gigabits per second. That's a big number. Oh, by the way the receiver sorts out the signal is now perfectly clear. Spatial Fourier transforms. Okay? All right. To make the link budget a little bit better, get more elements in to help me, Each one of these 16 transmitters and each one of these 16 receivers will in fact be a 16-element subarray. That gives me a bit of electronic beam steering, so it aims itself and it helps the link budget, as I've explained. Okay, let's do the link budgets. Let's assume we're doing a half a kilometer range. Let's assume 4 nines condition for rain, 50 millimeters per hour. Let's use industry levels of safety margins, manufacturing, beam blockage, aging. Then we do our link budget. If our receivers are 8 dB noise figure, then each of our transmitters needs to put out about 50 milliwatts. Okay, not quite as easy. I can't do this in CMOS. But I can, if you search the literature, you'll find dozens of published low noise amplifiers and dozens of power amplifiers that beat these numbers. Got it? So once again, I can build a system. There's no question. The question is, how much does it cost? And does anyone want to use it? In other words, are enough people going to pay to use it to make up for what it costs to make it? And today, unfortunately, the answer is no, but who knows what will happen in a few years' time. Okay, so am I crazy? And that's one of the best points in this, but we'll get to this in a moment, okay? You as students, ignore the professors for a moment. One of my main messages here is you need to stop listening to professors. That's not quite true, but you need to stop believing them. That's critical. You must not believe what people tell you. Is that clear? Okay, let's go through this, because I'm lying to you right now. Okay, all right, so let's compare the 220 gigahertz system to systems at 90 gigahertz and 35 gigahertz, all with the numbers I just gave you, and let's compare, do the link budget, and see how much power we have to radiate. And immediately comparing 220 gigahertz to 90 gigahertz, oh goodness, I need to radiate 10 times as much power. So this looks like a catastrophically bad decision until I realized that, oh, to do 80 gigabits per second per channel, I need 40 gigahertz of bandwidth with simple modulation. And there's a decent chance that the government might give me 40 gigahertz of bandwidth around 220 gigahertz, but there's no way they're going to give me 40 gigahertz around 90 or 40 gigahertz around 35 gigahertz. Spectrum is too valuable down there, too many people around. So if I look at percentage bandwidth and back off on keeping my percentage bandwidth the same, as I drop down in frequency, I must use less bandwidth. That means I got to use those more complex modulation schemes. The higher frequency has more atmospheric loss, and this term is worse. But if I'm forced to use more spectrally efficient modulation, then I'm winning because the low frequency systems are worse on that. And in fact, what happens is the high frequency system wins. Okay, so I'm a hero, and I'm a genius, and you should listen to me. Okay, but I'm a professor, and a professor is a salesman, and what do we know about salesmen? You should never believe them, right? Okay? You think I'm making jokes, I'm dead serious. Okay? I'm cheating because I've picked a number that makes me look good. I got half a kilometer range. So half a kilometer range, with this level of rain, I've got 20 dB per kilometer, so I've got 10 dB path loss. 10 dB is not great, but it's not terrible. You understand? It's enough I can make up the 10 dB with this here. But if I'd said 1 kilometer or 5 kilometers or 10 kilometers, then there's no way I'm going to make up the atmospheric loss with the spectral efficiency term. So simply, dB per kilometer times number of kilometers, how many dB is that? It's less than 10 dB, less than 15 dB. Good chance the high frequency system, I'm not saying it's going to be the winner, but it's a good chance that it's in the fight, worth further investigation. If it's 30 dB, forget it. You're fooling yourself. Okay, so back when we started, they were saying 5G is going to take over the world. Cell phones are at 5 gigahertz. They're going to do 28 and 39 gigahertz. Then we're going to do 75, so you professors need to do 140 gigahertz. When we wrote the Senate proposal, they said if you mention any carrier frequency below 100 gigahertz, we guarantee you won't get funded. Okay, so there we are. So I had ex-students at Samsung designing 28 and 39 gigahertz transceivers for the handset in the same period. And around about the time I bought this little beauty, it's an iPhone 13, pretty old I know, okay, you could pay an extra $300 US to get the 28 and 39 gigahertz transceiver in it. 3 or 4 years later, it's gone. 28 and 39 gigahertz to the handset was a failure in the US. Oddly enough, they're putting it back in here now. They're just putting it in saying, it doesn't cost too much money. Let's just see what happens. Okay, so 28 to 39 gigahertz to the handset was a commercial failure, so it seems to me that 140 gigahertz to the handset would be complete lunacy, right? Okay, First question, 50 gigahertz or 250 gigahertz? Here's our link budget, here's our atmospheric attenuation. Oh, our worst case atmospheric attenuation is the same at 50 gigahertz and 250. Now, if I'm looking at this term here, lambda squared over r squared, it's better at 50 gigahertz than 250 gigahertz, but I can win that back easily with a little bit more less spectral efficiency at the high frequency system. Then you're going to say, but you know, I'm a circuit designer. I know that I can build much better transmitters and receivers at 50 gigahertz than at 250 gigahertz. And I'll say, yes, but I'm a transistor designer and a circuit designer, so I'm going to work on making better circuits and better transistors because I'm in research. That's my job. So it's my job to fix that. So my statement is, in a few years, if it were that simple, 50 versus 250 gigahertz, about the same, okay? While I'm at it, I ought to point out that either way, it's 20 dB per kilometer. So someone says, terahertz wireless over kilometers with terabits. Dude, you're talking 20 dB per kilometer. If you're talking 3 or 4 kilometers, that's 60 dB, which is a million. You've got to radiate a million times too much power. Do the numbers, okay? Got it? All right, next question is, so we've realized that at least long term when we make the electronics better, 50 and 250 are pretty much equal. But should we do 50 gigahertz or should we do what the phones do now, 5 gigahertz? Okay, this is a harder thing. Let's suppose we're in the middle of the Amazon, not many people per square kilometer, right? Now let's suppose we're in downtown Sao Paulo or Rio de Janeiro, people packed in crazy, right? Take the number of people per square kilometer, multiply that by the probability they're doing this, which is somewhere around about 200%, I think. Multiply that by the number of gigabits per second they've got, right? Okay, what you've got there is the number of gigabits per second per square kilometer you've got to deliver. That's the information payload capacity. Okay, if that, oops. Am I doing that or is it doing that? It's doing that, okay. All right, so at least I can't take the blame, but it's keeping me awake, okay? All right, so if that number is low, Amazonia, you're not making a lot of money if you're the phone company. You can't pay for a lot of base stations, so they need to be far apart. If they're far apart, the link distances are long, there's no way you're going to use high frequencies. Now, suppose you're in downtown downtown Seoul in Korea, and they've got one of these boy bands, okay? Now, there's crazy number of people there. You've got a lot of gigabits per second per square kilometer. You're making a lot of money. You've got to deliver a lot of information. Your base stations can be close together. The radio links are short. I'm still not saying that you will use high frequencies, but there's a decent chance that you might. Okay, pause. I'm running in danger of running over time, and I'm talking to you like I'd never talk at a conference. I'm preaching, but I think it's important. I'm now talking to you like undergrads in my classes. Don't believe what people tell you. 90% of the technical literature is crap. That's conservative. 99 is close. You must think for yourself. When people tell you something is the next wave, you must crunch the numbers. Okay? Is that clear? 5G was a stock bubble driven by the companies trying to raise the stock prices. And I've been burned by this several times in my career, so watch it. Okay? Do the numbers yourself. Is that clear? What I'm telling you is my stuff, 100 to 300 gigahertz, is not necessarily useful. I'm being honest with myself so I don't waste my time. Is that clear? Because if I lie to myself, I'm the easiest person to fool. You got that? When you tell lies, the easiest person is to fool is yourself. And the usual lie is my research is important and I got to stick with it, rather than wait a second, is this useful or not? Is that clear? Okay, let's continue. So, and there's another application which I think is probably useful. I went to the Netherlands. I was invited to Eindhoven NXP in May, and they're interested in switching the car radar from 75 gigahertz to 140 or maybe even 200 gigahertz, because higher frequency gives you better angular resolution in a given physical size, and they can't do that by making the array bigger because the car manufacturers won't let them. Okay, so there's a serious interest in high-frequency automotive radar. Okay, let's move on to systems work. I'm doing okay on time despite all of these silly stories I'm telling. Okay, all right, when we started this work, People at the conferences said, this is ludicrous, it's not going to work. It's not going to work because if you're talking to many users, each one of these signal channels in your receiver is carrying a mix, a superposition of the signals from all of you, and given distortion, nonlinearities, cubic distortion, IP3, if you guys know what this means, even if I know mathematically what I need to do to sort things out, the distortion will make that impossible. Never going to work. They said, oh, the phase stability on these local oscillators is going to screw you up as well. So we got the theorists looking at the problem, and they said, you know what? It's probably worth looking at, but the fact is, this system is going to talk to 16 people, but it's got 32 antennas, so it's got 32 radios in it. So there are more radio receivers than the number of people the system is talking to. Think back to your analog to digital converter class. Do you remember oversampling? Temporal oversampling increases your resolution. This is hardware oversampling. And the hardware oversampling is averaging out the distortion of those channels, and it's improving it. And in fact, rather than being worse, it's easier. That's due to these papers by those other professors and students and other than my group. Okay? In a similar way, we found that the phase noise, the phase stability of the local oscillators is not the problem that people worried about. It's not easier, but it's not more difficult than a normal single-channel radio. Okay? Finally, I've already given the game away. Surprisingly, I've mentioned to you that the right way to resolve the signal as a function of direction from the signals at the antenna is to do a spatial Fourier transform. I don't have time to explain, but your Wi-Fi base station that's also doing MIMO is not doing it that way for reasons you can ask me about later. And these two people here, Madhav at UCSB and Christoph Studer at now Zurich, realize that, oh, this is a big mistake. You need to do spatial Fourier transforms. It's the computationally efficient way to do this. Okay, so the digital beamforming is like, oh my God, this is incredibly hard. It's going to take a supercomputer running a kilowatt to do these spatial Fourier, to do the beamforming. In fact, Christoph has built at Zurich chips that support 64 antennas, 32 people, net throughput of 46 gigabits per second. And it wasn't even in leading order CMOSs in 22 nanometers. Okay, so the beamforming is a solvable problem. Okay, again, not my work. Now let's talk about transistors. And I've heard that a lot of the circuit designers want to understand what the frequency limits of transistors are, so I've taken the risk of adding a bit more information here. Okay, here I'm showing you a performance scorecard. This is noise figure as a function of frequency, comparing different technologies. Gallium nitride HEMT, gold, indium phosphide, black is silicon CMOS, red is silicon germanium HBT. And what you can see, those three technologies are pretty much the same on noise as a function of frequency. If you look at the indium phosphide bipolar transistors, it's a little bit better than those three. And the winner is the indium gallium arsenide channel field effect transistors. Now what I'm showing you in these other graphs is efficiency of the transmitter on a log scale versus output power of the transmitter on a log scale, broken down for a fair comparison in narrow chunks of frequency. What you see is both CMOS and SiGe HBT are pretty good, up to about 140, 150, 160 gigahertz, but they die off after that. You see that the indium phosphide bipolar transistors are the champion in power and efficiency. Surprisingly, you see that the gallium nitride field effect transistors are in last place, which is quite surprising given that they're the leading power technology below 110 gigahertz. Here to give you a sense of what can be done, in indium phosphide field effect transistors, the Northrop Grumman folk have built transistors which provide power amplification up to 1.5 terahertz. And they built amplifiers at 1.0 terahertz. And they did that in 2015. That's 10 years ago. How old were you then? Okay. In terms of the indium phosphide bipolar transistors, the power gain cutoff frequency is a little bit lower at 1.1, 1.2 terahertz. These can take about 3 volts. And this was done in a collaboration between my group and Teledyne, a bunch of my ex-students there. That's 2011. That's 14 years ago. Okay, long time ago. If we back off to the 250 nanometer node, cutoff frequencies drop a bit, you get a bit more voltage. That's a nice technology for power amplifiers in the 200 to 300 gigahertz range. So not only are terahertz transistors feasible, but they're old news. This is old and boring. Okay, got it? All right, here are some circuits with that. Digital logic clocking at 200 gigahertz, an oscillator at above 650 gigahertz, amplifier above 650 gigahertz, transmitters and receivers in the 550 to 600 gigahertz range. These are hero experiments. The transmitter and receiver are both kind of bad performance. High noise on receive, low output power on transmit. It's just showing you can do it, but you've got to drop down in frequency if you want to get decent performance. You need to do that anyway because the atmospheric is not useful because of atmospheric attenuation at these frequencies. Okay. I was told that you want to know as circuit designers about a little bit about transistor high frequency limits, right? Let's do the bipolar transistor instead of the field effect transistor because it's easier. Bipolar transistor is brain dead simple. Ready? I got a transistor. I'm working at a certain frequency. I'm designing circuit. I want every circuit that I make to run at twice the frequency. So the transistor needs to give me the same voltage, current, resistance. Every capacitance has to get twice as small. Every transit delay has to get twice as small. Okay, let's play the game. Okay, ready? Okay, I've got an electron transit time in the base going as the base thickness squared. Okay, the base needs to get square root of 2 thinner. I got a collector transit time proportional to the collector thickness. Okay, I make that 2 to 1 thinner. Ready? Okay, I got a capacitance between the collector and base, which is epsilon A over D. I want that capacitance to get 2 to 1 smaller. Oh, I'll make the thickness 2 to 1 bigger. Oops, sorry, can't do that. I've already made the thickness 2 to 1 smaller. So what I'm left with is I have to make the area 4 to 1 smaller instead. You got it? Okay, I got a maximum current, it turns out, that's proportional to the area and the inverse square root of the thickness. That got 2 to 1 smaller. This got 4 to 1 smaller. Those precisely cancel. Whew. I've got the current I want. It didn't change. I'm okay. All right? I got a temperature rise. The temperature rise is proportional to the power, but it varies as 1 over the length and as the log of the length to the width. Hang on, what did I say? The area of the transistor's got to get 4 times smaller. Area is length times width. I better not reduce the length or the temperature's going to rise to crazy numbers. So I've got to reduce the width by a factor of 4. Okay, got it? 2 more things and I'm done. Is this okay as circuit designers? You don't like device physics? It's device physics for circuit designers, right? Okay. All right. My resistances surprisingly come not mostly from the semiconductors, but mostly from the metal to semiconductor contacts. So my emitter resistance is the contact resistance of the metal to semiconductor interface divided by the area. The area got 4 to 1 smaller, so the contact resistance between the metal and the semiconductor per unit area needs to get 4 times better. Okay? In the interest of time, I'll just say it quickly. The base ohmic contact, it's the same story. Bingo, we got it. If we want to double the bandwidth, we've got to reduce the feature size of the transmitter by a factor of 4. That's on line widths. We want to double the bandwidth. More or less, the semiconductor layers need to get 2 to 1 thinner. We want to double the bandwidth. The current per unit area has got to get 4 times bigger, but the current per unit stripe length stays the same. All bipolar transistors, silicon, indium phosphide, regardless of scaling generation, peak out at 2 milliamps per linear micron because of temperature rise. The current density has gone up by a factor of 4, but the punchline is we've got to improve our ohmic contacts, the resistance per unit area, by a factor of 4 every time we double the bandwidth. And we've got to do that while the current density is going up by a factor of 4. Okay, there's this great science book, Uncle Tungsten, by Oliver Sacks. Anybody know who Oliver Sacks is? No. Okay, cultural. Never mind. Okay, light bulbs. The old-fashioned ones, incandescent. They're metal that gets hot, right? You've got to use a really tough metal. They call these refractory metals. Iridium, ruthenium, molybdenum, tungsten. Okay, and I've forgotten a couple, but that's good enough, right? So not only do we have to do this, but there's got to be one of those metals, okay? And my group in developing terahertz bipolar transistors spent about 5 PhD years on developing refractory ohmic contacts with incredibly low resistances. Okay, so I've got to get out of this because we're going to talk about other things. So that's how we got to the 130 nanometer, 1.1 terahertz transistor. What do we need to do to get 1.8 terahertz? Well, we have built ohmic contacts to the base and to the emitter with resistance good enough for even the 1.82 terahertz transistors. This is exciting, right? Expect a line to come through the door in a second. Okay, so we know how to do this, but not in a transistor. We know how to do this on an The emitter is the first contact you make in the process flow. It's nice and clean. We can make as good a contact to a transistor emitter as to a test structure, but the base ohmic contact is made about a week into the process flow where we've generally made a complete mess of the waveform. It's got oxides and organic contaminants on the surface, and the only way to fix that is to punch through the surface of the semiconductor controllably with a metal that reacts slightly in. Okay. The problem with that is, although you say, it's only sinking 3 nanometers in a base that's about 17 nanometers thick, is in some sense that's not true. The only portion of the base that's heavily doped enough to get this contact resistance is about the top 5 nanometers. So we're sinking 3 of those 5 nanometers in there. So the next scaling generation where it gets thinner, it's not going to work. So the solution is to do in indium phosphide what they've been doing in silicon germanium for about the last 30, 35 years. It's called base regrowth. After you've exposed the base, you put the transistor back into a growth system and you grow more base semiconductors. And you dope the thing crazy heavily and you grow it real thick. So it's heavily doped for low resistance. It's really, really thick so that you can let the contact sink. But under the emitter where the current flows, the base is lightly doped, that gives us high current gain, and the base is very thin, which gives us low base transit time. Now, my PhD student funding had dropped off dramatically at this point. Government was getting bored with this. We built transistors with 64 nanometer emitter feature size in this process flow, and we've got the contact resistivities we need, but we ran out of money before we shrunk the whole transistor to the level that we needed to get 2 terahertz. But when I go home tonight to the hotel, I got to send marketing view graphs to my friends at Teledyne because they're still trying to get money to pull this off. Okay, so we're working to get money to do this to get the next generation node at 1.8 terahertz. Okay, got it? Okay, faster field effect transistors. I'm watching time. In the interest of time, I'm going to say, look, skip the details. It's a similar story, but a little bit different with the field effect transistors. Your scaling limits are 1, the gate dielectric. As you make that thinner, you get quantum mechanical tunneling leakage. The other is a semiconductor physics limit. Hold that thought for a second. It turns out that the insulator used by world record transistors was not the best choice. It was a wide bandgap semiconductor used as the insulator between the transistor channel and the gate. So we went in, and it wasn't easy, but we replaced that by a standard high-K gate dielectric from the VLSI silicon industry. And after a few years of effort, we were able to get a 1 terahertz power gate power frequency with that. Unfortunately, 1 terahertz is respectable, but it's not world record. I am also writing analysis and early stage of proposal writing with my ex-students at Northrop Grumman to take this, bring it into the Northrop Grumman process flow. And there's a couple of other fixes we need to do that are deep in material science in terms of the design of the channel material that are also necessary if we're going to push the cutoff frequencies into the 2.5 terahertz range. But it may be feasible. Okay, enough device physics. For a circuit designer, what do we want from the transistor? Okay, if we're building radios, what we need is low noise on receive, but the noise of a multi-stage low noise amplifier is the noise of the first stage plus the noise of the second stage divided by the gain of the first stage, the noise of the third stage divided by the gain of the first and the second stage. The gain at high frequencies is low, so you cannot ignore these other terms. Okay? This is called the cascading noise barrier. Okay? Right? On transmit, we want high power added efficiency. That's the difference between output and input power divided by the decent power. Because the gain per stage is low, we've got to use more stages to get the gain we want. Any stage has some variation of gain with output power as it reaches its limit, so that gets worse as you stack up more stages, and that becomes a big problem. It screws up your modulation. Okay, so once again, I need 3 hands, and if you'll forgive me, I need to steal your phone. Okay?
Go ahead.
Okay, I'll try to stay audible. So, I go to the conferences, and because the gain per stage is low, there are gazillions of papers on clever tricks to increase the gain per stage. So let's see, I'm in the Apple phone store, and this phone has more dB gain per stage than this one. So I'm going to pay an extra 1,000 Brazilian units of currency, right, for more gain per stage. Am I going to do that? If this had lower noise figure, that's more sensitivity, so that's more range from the base station. I might pay more for that. If it's got more output power, that's more range from the base station. I might pay for that. More efficiency is more battery life. I might pay for that. But gain per stage, you got to be kidding. So why are PhD students bragging at the conference and look, I've got more gain per stage? Okay, they're not thinking, right? Now, there are a variety of techniques for doing this, and I need to get on the next slide to do this. One is capacitive neutralization. The other is Sinhafer-Winter's unconditionally stable positive feedback from 1966, are ways of maximizing the gain per stage. This paper was forgotten for 30 years, and now it's getting lots of excitement and interest. Okay, I'll wrap up pretty soon, okay? If a paper's been forgotten for 40 years, what does that tell you? It was never important in the first stage. Why? Because gain per stage doesn't matter. House and Adler, two very famous people for other reasons, proved in 1958 that the thing you care about, which is cascaded noise figures and network invariant, meaning you can put a transistor in any circuit that's lossless, and you get that number. So in some sense, all low noise amplifier circuits are the same. We, in a much simpler proof, to the point that I won't brag about it, have proven that the graph of power added efficiency versus added power for a power transistor is also a network invariant. So in some sense, all power amplifier circuits are the same. You got it? So we actually pick our circuit topology based on simply which circuit topology, given that the tuning elements actually are lossy, gives us the lowest tuning loss, and that's it. Okay, got it? Okay, now on to examples, and I'll try to write up fast because I know you want to run and stream it. Here's a power amplifier at 150 gigahertz in the 250 nanometer technology, indium phosphide HPT, puts out a half a watt, and it's about 15% efficient. This thing is about 2 millimeters by 1.5 millimeters. Okay, here's an amplifier at 220 gigahertz with about 18% efficiency. The industry folks tend to laugh at you if you have an efficiency less than 30%. More than 30%, they start paying attention. Okay, so this is getting close, except that my own ex-student, I have no involvement, got 25% efficiency at 220 gigahertz. Getting real close. Okay, here's a low noise amplifier in the HPT technology, 5.5, 6 dB noise figure at 220 gigahertz. Won't beat a good indium phosphide field effect transistor, but it'll beat absolutely anything else. Okay, here are transmitters and receivers, 200 gigahertz transmitter receiver, 280 gigahertz transmitter receiver. What's inside the box? Well, you've got a frequency multiplier chain. The 200 gigahertz transmitter, you start with a local oscillator at 25 gigahertz. You multiply it by 8 to make 200 gigahertz. This little gadget makes sine and cosine. You mix sine and cosine against your baseband digital data, add them up, power amplifier, and out you go onto your antenna. The receiver is basically the same block diagram with the signal flow in the opposite direction. Okay, got that? Okay, now let's talk for a minute about array geometry. I'll move as fast as I can. If we are building a radar system for a jet plane, the radar beam needs to steer horizontally and vertically over 180 degrees. To do that, I need to have a two-dimensional array, and the elements need to be a half a wavelength apart. The problem is that high frequencies, a half a wavelength is not very big. So the element spacing is tiny, so we've got no space left to fit the electronics. And even if we did, the power density would be crazy high and would get really hot. Okay, this is the 2D array design problem, which is a killer problem at high frequencies. It's so important that it's critically also to understand that many systems you don't have to solve this problem. If I'm building a base station that talks to a bunch of people on the ground, there's no one floating in the sky, there's no one in the hologram. I don't need to steer my beam vertically, I can just steer it horizontally, and I can do that with a linear array. And with a linear array, there's lots of space on the sides of the antennas to build your electronics and to put in the heatsink. If I'm doing a which is exactly what you need by accident for high-frequency connections. So these VLSI packaging technologies are perfect at high frequencies. The problem is not the unit cost, but the initial prototypes will cost you $100,000 to $200,000. You can't afford them. Okay, so very quickly, I'm wrapping up now. Here's one of those base stations, a prototype at 140 gigahertz. 32 element arrays the target, break that into 8 element units. There's 8 antennas, 8 indium phosphide power amplifiers, 8 CMOS transmitter ICs. Samsung has done link demos at 140 gigahertz in the gigabit per second range. If we go to 200 gigahertz in the backhaul, this slide is the one that I just showed you. I'm just reminding you of it. Here are the 200 gigahertz transmitter and receiver ICs I just showed you. We're wire bonding those to a little piece of quartz that's got 4 antennas on it. All that's doing is getting the signal up into air and off the wafer. Then we catch the signal with a Teflon lens and focuses it. And then we build a link from transmitter to receiver. We're doing this inside a room because we don't have the government license to do it outside. We have to attenuate the beam with a stack of paper so the receiver doesn't overload. Doing 32 gigabits per second with it. Okay? I talked about spatial multiplexing. Please don't post a recording of this on the web because this is unpublished. They'll pull the conference paper. Here's a 2-element transmitter and a 2-element receiver of the same. And over 7 meters, we're doing MIMO and that spatial Fourier transform to recover the data, and doing that at 2 channels at roughly 32 gigabits per second per channel. We could do 4 channels there, but we only have 4 transmitter and 4 receiver modules, and in the course of the work, we kind of broken 2 of our transmitters. Okay, it's crazy hard to build this kind of hardware. Okay, what's next? Okay, we need to, I mentioned that you don't always need 2-dimensional arrays, but plenty of times you do. So we're working right now on 220 gigahertz array at half wavelength pitch. That's a crazy hard exercise in fitting circuitry for the transmitter and receiver into tiny areas. Okay? We are working on more efficient power amplifiers at these various frequencies. We've taped out designs that should do almost 30% at 225 gigahertz, around about 22% at 280 gigahertz. We're really, really hoping that these come out close to simulations. You know, this is sort of saying, okay, this is production, sort of product level performance at 225 and getting close at 280. Basically, the point there is you're taking these high frequencies and saying, not this is some basic research, but we're getting close to the performance you'd need for real products. Okay? Dropping down to 75 gigahertz, remember what did I tell you? 28 and 39 gigahertz was a failure because the tolerance for beam blockage, because the range was too low. Okay, so if we're going to make even 28 and 39 or 75 gigahertz work, we've got to do something about that. And what we need to do about that is increase the number of transmitter and receiver elements, because that'll give us more receive power. The trouble is, if we have more elements in our transmitter and more elements in our receiver, that's more silicon area, that's going to cost us money, and it's going to burn more DC power, and so our battery's going to die. So what we've got to do is increase the number of elements while dropping the die area per element and while dropping the DC power per element. Unfortunately, we've screwed up the digital control on this thing twice. I'm losing my mind. We're going to get beaten by the competition. But these 75 gigahertz designs have 1/5 the die area and 1/5 the DC power per channel of published work. Okay, got it? Okay, there are other applications, high-speed data links. I'm very excited about building transceivers, transmitters, and receivers for optical links in the 800 and maybe 1600 gigabit per second range, right? 1600 gigabits per second with PAM4 is only DC to 400 gigahertz. We've done plenty of 600 gigahertz circuits. 400 gigahertz is, maybe I'll wake up. Teasing a little bit, but I think we can do it, okay? All right, so why do this stuff? Large bandwidth, massive spatial multiplexing sounds really good. The problem is limited range and easily blocked beams. The bad news is today we don't need it because the payload capacity society needs gigabits per second per square kilometer is not there, and because the range of these systems is too low and they cost too much money. So in working on these systems, not only do we need to increase the data rates, but we need to increase the range, we need to reduce the power consumption, we need to push up the number of elements to allow us to do that range. Okay? All right. Sorry to have kept you so long. Thank you so much for attention. Hopefully I'm not being completely boring. Thank you. Okay. ask me questions, professors are not allowed to answer. Of all the things I told you, what's the single most important thing? It's a lie. You must think for yourself. When you turn on the radio, now we have, you know, these streaming services, but when you turn on the radio, the rock and roll is crap. You keep changing the radio stations until you find the rock and roll that's worth listening to, right? 99% of rock and roll is crap. 99% of technical papers are crap. It doesn't mean you don't read them, but you need to keep changing the station and you have to evaluate by using your own logical thinking capacity and your own training in math and science. Above all, you should never believe me. Don't believe any professor. Work it out for yourself, okay? Got it? Thank you. Questions?
You talked about oversampling by a factor of 2 to 1 in arrays for improving the noise that is received.
Reducing the distortion.
Yeah. I'd like to know if that number 2 to 1 is a specific number that with experimental data, or it was like, okay, we think 2 to 1 is good.
So several things. It's entirely a theoretical calculation insofar as it's so hard to build hardware we don't have the experimental data to show it. Now, the underlying question you're writing is, in a massive MIMO system, what ratio should you have between the number of digitally steerable channels and the number of people that you're talking to? And the system theorists are all over the map with that, and I'm not sure I understand their arguments. So it's an excellent question. It's hotly debated in the literature, and unfortunately I'm ignorant of the proper case of the argument. To me, I want as large a load factor as I can because the electronics on these things cost money. Okay, but maybe I'm wrong. I don't know. Yes, other questions? Yes.
Thank you, Mark, for your nice presentation. I would like to know from you the electrical modeling of this terahertz device, because there's a huge problem in the carriers inside the base, for instance.
Okay, so the question is electrical modeling, and it's fascinating. I don't speak Portuguese, so I didn't hear the discussion on the last talk from Enritza Wiltron. But just to give you my credentials, that instrument they're showing is out of my lab. They put an engineer into my lab at UCSB 20, 25 years ago and transferred the technology. So we've been working on very high frequency measurements, both building the instruments and using them to characterize transistors for a very long time. Okay, got that? Now, with that as credentials, in testing a transistor with a 1 terahertz power gain cutoff frequency, even today when there are network analyzers which will do one-way for measurements to 1.5 terahertz, that's not how we do it. Because as you go up in frequency, if you only stop at some percentage of the transistor cutoff frequency, you've got to extrapolate your model. Ooh, that's bad. But the higher frequency you go, the less accurate your measurements are, and your accuracy is degrading faster than the level of your extrapolation. So 20 years of experimental experience at both UCSB and Teledyne, and we do not use these ultra-high frequency measurements to develop our transistor models. We basically use DC to roughly 110 gigahertz because the accuracy is degrading too fast. The thing about transistors is they are very small as a fraction of a wavelength, even at 500 or 600 gigahertz. So charge-controlled and lumped element models and extrapolation in frequency still work very well. Okay, so the major modeling problem we're having is the inductance of the base lead of the transistor is a bit of a headache, and that is sort of empirical fitting. Okay, but other than that, the extrapolated measurements work very well. The Keysight ADS design environment, which integrates mass layouts and detailed E&M simulation, if you know how to do that, I don't, but some of my better ex-students do, is really, really good. So, you know, we will do a 300 or 400 gigahertz amplifier, and the gain will be off by a dB, and the center frequency will be low by 5%. That's all. It's that good. I think if you're designing something at 600 gigahertz, then the errors will be larger, but this is widely misunderstood. With modern grade metrology, modern grade E&M simulation tools, the design flow of even multi-100 gigahertz ICs is really, really good. Yeah, okay. Yes, thanks. Question?
Forgetting for a moment about the fabric. All right. Forgetting for a moment about all the difficulties you have for manufacturing such a device, have you ever thought about having some kind of waveguide or some kind of refractory material that could modulate somewhat the incoming signal so that you could spatially divide the array?
Oh, okay, so doing beamforming, not in digital signal processing.
Yeah.
So oddly enough, at the day before yesterday in Brasilia, they weren't doing it at 300 gigahertz, but at 67, 75 gigahertz, they're doing exactly that. They had an array of passive antennas with waveguides coming into a little block, and they had a little array of liquid crystal, and they're applying bias voltage, and they're doing beamforming that way. Yes. So it depends on the high frequency losses of the material that's giving you the variable dielectric constant, and it depends on things like the IC count and the cost per IC. What's the power consumption limit? What's the DC powers? It's an excellent question, except you have to understand that if you don't have an incredibly low loss variable dielectric constant, then forget it, you're not even in the game. But yeah, it's a possibility. So you can't do multiple simultaneous beams that way. They're trying to do multiple simultaneous beams by basically, the other way of doing passive multiple simultaneous beams is to do it with lenses. So I've got a lens and I've got a bunch of receivers. It's called a focal plane array. Then, without any of this nonsense, I can separate my beams. There is the physical equivalent of a lens in transmission line networks called a Rotman lens or a Butler matrix. And so these are other approaches. More detailed discussion will bore the heck out of the rest of the audience. But yeah, it's an excellent question. Thank you.
Thank you so much. Pessoal, vamos dar uma salva de palmas para o